Okay, so let's begin.
Okay, all right. Maybe I will share my screen.
Yes. Okay.
Okay. So,
Welcome everybody to this fixed Majorana-Raychaudhuri seminar series. Our first speaker of today is Ramkishor Sharma from Czech Republic, Prague, and he's going to talk about generation of magnetic field during inflation. So I'll send you a reminder when 5 minutes.
okay, sure. So I start then.
Yes, yes.
Yeah. Okay. All right. So first of all, thank you so much for this opportunity, and it's a pleasure to talk about some of my recent works on this seminar series. So today I chose to talk about some generation mechanism of observed large-scale magnetic field in the universe, and particularly I will be talking about the generation mechanism during the epoch of inflation. So here is the outline of my talk. So I will first provide some motivation why one is interested in looking at magnetic field generation early in the universe. And then we'll talk about in general what are the problems with the generation of magnetic field during inflation, and highlight one of the work which gives a possibility of generating magnetic fields. And then if time permits, we'll also talk about some development in the context of action U1 inflation, and can one realize magnetogenesis in this model of inflation. And then we'll go to a very recent work of ours where we look at the magnetic field generation in a action SU2 dynamics during inflation. And let's see how much I will be able to tell within this time limit. All right, so magnetic field has been observed over a large scale in the universe, and it won't be incorrect to say like wherever one has tried to observe the magnetic field in the universe, they have found the presence of magnetic field. It is primarily has been observed by synchrotron emissions and the Faraday rotations. And if you look at the collapse objects like galaxy and galaxy clusters, the typical magnetic field strength observed in the galaxy is roughly 10 to tens of microgauss, and this is typically ordered over the size of galaxy. To give you an example, this is an image of an optical image of M51 galaxy with radio contours, white radio contours, and then no headed arrows shows the distribution of the magnetic field in this galaxy. And as you can see, this is typically ordered over the size of the galaxy. If you go to the large structures like clusters of galaxies, similar magnetic field has been observed and typically ordered 10 to 20 kiloparsecs. However, if you go to a regime which is far from these collapse objects, like in the intergalactic medium, it is very hard to observe magnetic fields, but there has been some indirect inferences for the presence of magnetic field in these regimes, and that puts a lower limit, says that the magnetic field has to be above 10 raised to minus 16 Gauss if it is ordered or in a scale of megaparsec. So the natural questions to ask here: how do such large-scale magnetic field arises? And they can be well explained by, let's say, once the structures start forming, there can be some seed field generated during the structure formation, and later can be amplified by something called dynamo, which converts some of the kinetic energy to the magnetic energy, and can explain the presence of this microgauss level magnetic field in the collapse objects or structures like galaxy and galaxy clusters. However, if you look at this presence of magnetic field intergalactic medium, astrophysical mechanism may not be able to explain their presence, or may not be generate the magnetic field which satisfy the lower limit put by these GeV observations of the quasars. And that motivates the study of magnetic field early in the universe, and one can derive this generation mechanism in two categories, broadly during inflation and during a phase transition. In this talk, I will primarily be talking about the generation of magnetic field during inflation. An idea here is it's simple. It's like since inflation provides a natural setting for the origin of these small density fluctuations, which later collapse to form the structures in the universe. So, and this origin of structures is related, origin of this density perturbation is related to the quantum mechanical nature of a scalar field, which can itself be inflaton or can be any other scalar present during inflation. So, a natural question to ask: what happens to the electromagnetic fluctuation? And it turns out to be that it is not possible to generate magnetic field looking at this quantum mechanical nature of the electromagnetic field, and this turns out to be because of the conformal symmetry. And I will highlight in the next slide more about that, just to give you an intuitive way of, let's say, what happens. So basically, this, and don't take the numbers on this figure seriously, they are just for illustrative purpose. So on the x-axis, I have some scale factor, which is just give you a direction of time, and on the y-axis, I have plotted scalar electromagnetic fluctuations for a particular scale, which crosses the horizon during this time. So if you look at the scalar fluctuation, which has been shown in this blue curve, so if you, when this scale is well inside the horizon, this decays, but once they crosses the horizon and they see this horizon scale, and then they does not further decay, and that happens to each mode, and that's why, and the amplitude at a horizon crossing is roughly similar to other scales, and that's why you get a roughly scale invariant spectrum for the density fluctuations, which later forms the structures in the universe. However, if you now look at the electromagnetic fluctuations, and due to this conformal symmetry, they don't see this scale. So what happens? The vector field, when they were decaying, when the mode was like sub-horizon, but they continue to have the same behavior even after crossing the horizon, since this horizon scale does not play a role in the evolution of the vector perturbation. So to highlight this and to give you some quantitative estimate, so if you look at an inflation which happens, let's say, around in a scale of 10 raised to the 14 GeV, and look at the magnitude of the electromagnetic fluctuations for a particular scale when it crosses the horizon. So roughly at the horizon cross, this magnitude, if you calculate it, what it will be equivalent to the present day, in terms of the present day magnetic field, it will be roughly 10 raised to minus 10 cos. However, since this behavior continue, I mean, this decay continues even after crossing the horizon, and if you are interested in some astrophysical scale, let's take for an example of megaparsec scale. And if, let's say, you have a 60 e-folds of inflation, megaparsec scale will be crossing roughly around 10 tens of e-folds, 10 of e-folds, and then there are 50 more e-folds to go, and this magnetic field decays as 1 by a square. So once you, let's say, incorporate this further evolution, there is an additional dilution that is equivalent to 10 raised to minus 46 factor. So at the end of the day, you get a very tiny magnetic field due to this conformal symmetry. So if one wants to generate magnetic field during inflation, one has to get a way to break this symmetry. And I will talk about that in further slides. Before moving to that, I will just would like to give some useful definition, which I will be using later in my slides. So I will be talking about a lot about what is a scale invariant spectrum. What I mean, so basically, if you look at the magnetic field energy density, you can write in Fourier space as a logarithmic wave number space, and then this will and if it is proportional to k raised to power 0, that simply represents you have roughly same power at each scale, and that is what I mean by the scale invariant spectrum. A number to have in mind, and if you calculate what will be the strength of magnetic field if you equivalent to a magnetic energy equal to the CMB energy density, and that will give you roughly 3 microgauss magnetic field. So it's just giving an idea, since magnetic field also decays as a square, or the energy density decays as 1 by a for like radiation. So if early in the universe you have some, let's say, some small fraction of the total energy budget in the magnetic energy, that would also should be sufficient to explain the magnetic field strength in the present day universe, as radiation and magnetic field will behave in the same manner and their ratio will remain a constant. So that's why yeah.
Can you hear me?
Yeah, I can hear you.
Yes. So I have a question. Can I ask it?
Sure, please go ahead.
So when do I get the scale invariant magnetic path spectra? Is there any condition to get this?
So yeah, I mean, that depends on the model, but you can get it in the sense that, like in the case of density fluctuations, if you get a
Density
similar
fluctuation I
behavior.
get, but I'm saying magnetic path spectrum. When do I get?
Yeah, so I will talk about that in the next slide.
Okay.
One of the realization. I mean, it's a phenomenological
Okay.
realization where you can have scale invariant magnetic field spectrum, but I will also highlight there are problems with that. Okay, so if you just wait for maybe 2-3 slides. Okay. Yeah.
Thank you.
Yes. So, all right. So, as I highlighted earlier, that this conformal invariance of the electromagnetic standard electromagnetic theory basically need to be broken to generate the magnetic field strength of astrophysical interest. So there has been various suggestions in the literature. And so one of the possibility, if you break it by taking some additional couplings with some scalar coming from the gravitational side, or taking a model where you have x shown as the inflaton and then x shown photons coupled by these phi ff tilde terms. And there can be some where you modify the kinetic term by taking an additional coupling with a scalar present during inflation. It can be in inflaton itself or any other scalar. So I will talk about this third possibility first. So that model is like you modify your standard electromagnetic action in this form, where you take an additional coupling with a scalar. Yeah, so you take it in the this way that you don't want to break the gauge invariance, but you want to break the conformal invariance. So if you look at now this function and look at just the phenomenologically, let's say you take different time evolution of this function. So and ask this question: is it possible to have a scale invariant magnetic field energy density spectrum, which has been asked also earlier. So there are two possibilities. So either if this coupling function grows as a square or decays as a minus 3. So a here is the scale factor during inflation. So these two possibility will give you a scale invariant spectrum. And what exactly these two possibility will be doing? So you will be having a behavior of the evolution of the electromagnetic fluctuations now in a way that it is decaying, and once it crosses the horizon due to this additional coupling, it starts seeing this horizon crossing, and the behavior of the electromagnetic fluctuation will also become that they becomes constant. So they whatever is the amplitude at the horizon crossing, that remains same, and that's why you get a scale invariant spectrum, and that happens since each scale. So now in this case, if you take an example now, an inflationary model which where Hubble parameter is 10 to 14 GeV, then you will get a magnetic field of 10 to minus 10 cos, and that will satisfy more or less even the magnetic field observed in the collapsed objects, and also satisfy the lower limit in the intergalactic medium. And this seems the end of the story if you can realize a model where your coupling functions evolve in this way. However, the story does not end here, and it has been realized in 2019 by a paper uh, that these two models are not free. These two models have some problems, and since we were only looking at the magnetic field until now, so what happens to the electric field in this case now? So if you look at now the electric field and take this possibility where F is proportional to A minus 3, here, then it turns out that electric field diverges, and it can even overshoot the total energy budget during inflation and the inflation in between. So that is known as the back reaction problem. Now, if you look at the other possibility where F is growing as A square, and since at the end of the inflation, you want to recover the standard electromagnetic theory, so your F should be 1 at the end. So it means your F will be very small at the beginning. So effectively, in this theory, if we now look at the coupling between the gauge field and the charge field, that will be very large, and even theory will be in the strongly coupled regime. That is known as the strong coupling problem. This has been highlighted in this paper in 2019. So during my PhD, we looked at, we looked at this phenomenologically. Is it possible in some way that one can avoid these problems and get some magnetic field of astrophysical interest? So what we did, basically first we put this condition that this evolution of F does not end by the end of inflation, but let's say before the reheating we have a intermediary matter dominance era from the end of inflation to the reheating, and then F even evolves during that epoch. So what we say, let's say F is 1 at the beginning, and it grows as A square throughout the inflation. So you will have a scale invariant spectrum at the end of inflation, no strong coupling, no back reaction problem. But since your F will be now very large at the end, so effectively coupling between the gauge field and the charge field will be very small, and your theory will be in the weakly coupled regime, but you want to recover your standard theory. So we had this post-inflationary matter dominance era where we say that in this era F decreases and comes back to this initial value. So in this at least realization, there won't be any strong coupling and back reaction problem, but one has to see when F decreases during this post-inflation era, what happens to this generated magnetic field. And also you don't want to overshoot the total energy budget, so that puts a constraint on this evolution of this post-inflation evolution of the coupling function. So what we found, first thing is that there won't be any scale in the spectrum now, since the branch which was giving the scale in the spectrum during inflation now decays, and you will get a blue spectrum. That's first case. And if you want to have a magnetic field of astrophysical interest, so this is a figure from one of our paper, and in this we plot this reheating temperature on the x-axis, and on the y-axis we have the generated magnetic field strength in our model. This black line shows here the lower bound on the magnetic field strength, which I was mentioning earlier in the intergalactic regime, and the red dashed line shows the magnetic field obtained in our model. So it says that if you want to realize this, at least satisfy this bound, then reheating has to be very low. I mean, it has to be below some 10,000 GeV. So we find that, yeah, so there is a viable model, but it comes with two things. One is it won't have any scale in the spectrum, it will have a blue spectrum, but still it can satisfy the lower bound, but then reheating has to be at a lower scale. Sorry. So let me just summarize this part until now. So what I'm saying, that indirect influence of the presence of magnetic field in the intergalactic medium demands some generation of magnetic field early in the universe, as it will be very difficult to generate these magnetic fields by some astrophysical mechanism. And inflation provides a natural setting, and these initial proposals, although they had this strong coupling and backreaction problem, we looked at those problems and tried and give a phenomenological model where it is possible to generate magnetic field of astrophysical interest, but it requires a low reheating scale. So what are the things which one needs to address? One of the things is, like, one has to address a realization of such a scenario where F increases during inflation and then decays in this post-inflation era in a basically model of inflation. And furthermore, we also looked at like if there are these primordial magnetic field generated, they will have non-zero anisotropic stresses, and then they can source the production of gravitational waves. And for some scenarios where reheating happens, let's say around 100 GeV or even lower at, let's say, QCD scale, then they can give some gravitational waves in the millihertz and the nanohertz band. And if they have observed in the future, then can also be used to at least rule out this possibility, or at least put constraint on the parameters of these models, independent if one's realizing in a model of inflation. So in a recent study, we looked at, I mean, one more point to highlight here. So as I said, this requires these ADO couplings. In a recent work, we looked at a generation of magnetic field in a model of action SU2 inflation, which does not require any ADO coupling, and I will say more about it in later slides. So maybe I can just pause here for a quick question and then can move to the second part. Check the time, how much time I have. Okay, good. All right, so let me move to this second possibility where one wants to look at the generation of magnetic field in axion U1 inflation. So let me first keep this part of magnetogenesis aside, and let's talk about what is this model of inflation. So the first of such model has been proposed in this paper in 1990 by Catherine Fries and collaborator. And there was no U1 field, it was only axion field with cosine potential. Later it was realized with the CMB data that it is not compatible with the CMB data. Either you have large tensor to scalar ratio or different scalar tilt, which doesn't satisfy the CMB data. But then there has been various suggestions to make this model viable with the CMB data. So one of the model comes where you allow some additional dynamics in the form of that your axion field couples to some U1 field, and once you have this additional dynamics, there may be a possibility that it may satisfy these CMB data. And so idea here is that once you have this coupling, and then this once the axions rolls, they can lead to the amplification of the gauge field. So here, due to this term, this will give you an instability in one of the electromagnetic mode. And once it is, let's say, it grows exponentially. Let's say if the energy budget of this becomes significant, that the back reaction of this on the action dynamics becomes important, then it can affect the action dynamics, and you can have a longer duration of inflation and also maybe satisfy the CMB data. So I would like to highlight this recent work where the authors have looked at this scenario where you have this additional dynamics coming from the U1 side, and then what happens, what is the status now with the CMB data. And they found that if this coupling between actions and the gauge field is very large, like of this order, then there is a possibility that it will be within the, I mean, it can satisfy this Planck constraint on the tensor to scale ratio and the scalar spectral rate. One point to highlight here, since this model, I mean, this, once you want to make this compatible with the Planck data, you require this large couplings. In this study, the authors only considered the homogeneous action case and neglected the inhomogeneities of the action fields, but that will also be important, and there can be some changes to this conclusion on this, that on this model of action U1 relation once you try to make it compatible with the Planck data. So we looked at this phenomenology on the lattice simulation, and we are not the first ones, but it has been looked at it by few groups in the last 3 to 4 years. That the whole dynamics, where you also incorporate the action inhomogeneity, but on the lattice. So idea here is that you have this action field. Once it rolls down, it amplifies the gauge field, and this gauge field will back react on the action field, and that can also first of all lead to the enhancement of the action inhomogeneities, and which can lead to the formation of primordial black holes. So that will give you one channel to constrain the coupling between action U1. Other channel, once you have this amplified gauge field, can also produce the gravitational wave. The gravitational wave will be very high frequency gravitational waves, and you can use the ineffective constraint to constrain the coupling between actions and U1, and this has been done in the literature. I will not be going into the detail of the constraint on the coupling, but I will only focus on the magnetogenesis side on this in this talk of this action U1 inflation. So we solve basically the dynamics of action field and the gauge fields on the lattice. And let me just quickly show this the dynamics of this model for different couplings between actions and U1 field. So let me start with this case where you have not very large, I mean, not coupling is not that large that the back reaction becomes important during inflation itself. So what I'm showing here in this panel A, we have energy density. So basically the red curve is the potential energy density, and the dazed yellow curve is the kinetic energy density of the action, and the blue curve is the electromagnetic energy density. So in this case, the end of inflation is a usual end of inflation when the potential energy becomes roughly equivalent to the when the kinetic energy becomes roughly equivalent to the potential energy of the action field, then there is an end of inflation. But gauge field is also amplifying, but their back reaction will only be important in the later stage after inflation. But you have a larger coupling case where, let's say, this value is 90 or even intermediate here, this is for 75. Then the gauge fields can be amplified so much during inflation itself. So basically, I should mention here that these vertical gray lines are representing the end of inflation. So what happens here, since rolling of action was, I mean, once action was rolling, and the parameter which governs the growth of the gauge field is the velocity of the actions. And if it is larger and the coupling between action and U1, so it becomes, let's say, large enough, then it will back react and will reduce the velocity of the actions. And then there will be also the further production of the gauge field will also be reduced. So in this case, now the end of inflation will be decided not by the kinetic energy of the action, but once the electromagnetic energy density and the potential energy becomes roughly equal to that will decide the end of inflation. So if you look at some points to highlight here, maybe in the interest of time, I will not talk about much. But if you look at the slow roll parameter here, which and we decide, I mean, the end of inflation is decided by when it becomes 1. So just look at the two cases here. So one is the red curve and the other is the green curve. So green curve is the case when you neglect the action inhomogeneities, and the red curve is the when you also incorporate the action inhomogeneities. So basically now the duration which get extended because of the back reaction of the inflation can be different once you take the action inhomogeneities into consideration. So just this is the part about the action, this dynamics of this model. So now let's look at if these gauge fields are produced, can they give you large enough, large enough magnetic field which can satisfy these lower bounds in the intergalactic regime, in the intergalactic medium. So let me just directly go to this table, and we found that if the coupling between action and U1 is large enough, then the produced magnetic fields, if you look at it here, and this is the bound coming from this Blazer observation, they are above this bound, and there is a possibility that they may explain these magnetic fields in the intergalactic medium, this model. So summary here of this part, that we study this U1 field dynamics of the natural inflation, and which basically can also make this model with the compatibility with the CMP observations. And there is a possibility to have large enough magnetic field in this model, but this is possible for large coupling cases. However, I would also like to point out here that since these produced magnetic field are not well above the bound, they are just marginally above, and in the with the future missions, this bound will also get improved. You will have a higher, basically lower bound, and if it becomes above than these values, so this scenario can also be ruled out by these future missions. But these magnetic fields are like very small. I mean, they peaks roughly at the parsec scales, since this is typically the peak is at the horizon side at the end of inflation, and if the end of inflation is large, end of inflation is, let's say, if inflation happens like at a large energy scale, then like 10^14 GeV, so these will be this coherence set will be small. Another point to highlight here, so we have neglected now the dynamics of the charge field, but once you produce a gauge field, the charge field also can play a role. I mean, they can be production because of the Swinger mechanism, and they can also affect the dynamics further, and can also may have this even a smaller magnetic field, and that may already be also below these bounds once you incorporate the charge field, but that is something work under progress, and we will report that soon. Okay, so in the remaining time, let me now quickly go through this possibility, although I don't know how much I will be able to tell about this. So we recently look at this model where you have basically, again, some additional dynamics in the action inflation, but now instead of U1, you have an SU2 field, and this has been proposed in these papers in 2011 as a, realization of inflationary dynamics early in the universe. This comes with the name of chroma natural inflation. And later, these authors also find out that, but this model is also not compatible with the CMB data set, and these are the observed NS and R values for different parameters of this model, and this is well outside this CMP data. But later, some of the authors look at this as an spectator dynamics. So I personally take it in the way that this question can also be posed in a way that if there are these additional SU2 field present in inflation, is there a possibility to maybe say about something about these fields? So these authors looked at this dynamics, and they found that, let's say, if this does not govern the, basically these are not the, let's say, dominating the energy budget and are not responsible for the inflationary dynamics, but let's say they are present during inflation. And there is an interesting dynamics comes into picture here, that you produce this SU2 gauge field, and which can produce these gravitational waves. And these gravitational waves can also, for some parameter space, can also be give you larger tensor to scalar ratio, and can also be probed by future CMP mission, and gives you a possibility of let's say, probing such dynamics during inflation. So this was the idea. So we started looking at this model from the point of magnetogenesis, but we realize is that if you want to look at this model to realize the magnetogenesis, one has to study this model in the larger coupling case, and I will say what I mean by the larger coupling case. But before that, I will just talk about what is the dynamics of this action SU2 expected action SU2 model. So basically, in this case, one thing is that you can have this SU2 field and can have an isotropic solution in this way, and it turns out to be that if you start with this solution, that this gives you an attractor solutions. And so just to show in this plot, so basically this is showing for one of the case, just look at the blue curve here. So if you start with this attractor solution, or the system will go to this basically attractor solution, and it remains, so basically Q remains constant, and then actions evolves with a constant velocity. So this was the background dynamics. So we are only looking at, we are neglecting the perturbations. We are not considering the perturbations of this SU2 field or of the action field. We are just looking at the homogeneous action field, and then this isotropic part of the SU2 field, and then this dynamics comes into picture. And this has been studied in the earlier literature. But what we studied, so once you now look at the perturbations of the SU2 field, I mean perturbations in this model, and they can also be amplified due to this background dynamics of this isotropic part of the SU2 field. And those are, I mean, if you look at the tensor perturbation, those are the ones which will give you these gravitational waves also. But in the earlier literature, back reaction of this perturbation was not considered. So we started looking at this scenario that once the back reactions are important, and what will be the dynamics. So what we realize now, let's look at these other curves, which are like green, black, and red curves. So basically, we start the system in this attractor solution, and then these perturbations get amplified and they back react and led to the system to go to another attractor solutions, and that's what we found. And if you look at the dynamics of the action field, this is like action goes with a constant velocity, but then it goes to another branch which is a constant velocity, which has a lesser speed of growth of the action field. So if you look at in terms of, let's say, the different terms contributing in the evolution of these action and SU2 background parts. So once the system is in the basically let me just look at the time. When the system is in this first attractor, so what is happening there? So you have a balance between this nonlinear term and the term because of the coupling between actions and this SU2 field, and that's basically governs the dynamics. But once you basically amplify the tensor perturbations, and then the tensor perturbation, the back reaction term will also be important, then the balance between the balance will be decided by these Q cube terms, and then between these terms coming from the perturbations in the evolution of these backgrounds. So basically now if I look at these perturbations, which are the basically we are only looking at the tensor perturbation of the SU2 field now. So basically we are studying the system in perturbatively. You have this background isotropic part of the SU2 and the action homogeneous part, and then you have these different perturbations of the SU2 field. So we look at this tensor perturbation, and we found that in the cases when the back reaction of the perturbation is important on the background evolution, you found that there is an interesting solution where this tensor perturbation amplitude after crossing the horizon remains constant. And I will say, I will not be able to go into the details of this, but this behavior interests us to look at the basically magnetogenesis aspects in this model. So to realize the magnetogenesis, what we say, if one identify this SU2 field with a standard model SU2 field, I mean, it need not to be, but once you identify with this SU2, the standard model SU2 field, And then at the electroweak phase transition, some of the part of this SU2 field will go to U1 field. And that was the realization. And we look at for the parameter space where this SU2 field is the standard model SU2 field. And we found that, I'll just be maybe quick about this part, that there is a possibility now to generate magnetic fields of astrophysical interest and which has coherence length like large enough, roughly like megaparsec orders. So these are few scenarios where I've shown the magnetic field spectrum generated in these models. And this we just put on these different observational limits. So these are the limits on the intergalactic, lower limits on the intergalactic magnetic field, and these are some scenarios, magnetic field generated in our model. But does the story end here? So there are few caveats in this. Maybe let me skip this part of the generation during phase transition and go to the summary of this part. So I would like to say that this axion SU2 dynamics does not require any ad hoc couplings to generate magnetic field, but we only study the system in the perturbative regime. So we have a background and then we are studying the perturbation, but we are studying a regime where the backreaction of the perturbations on the background is important. And we find that there is this second attractor solution, but all these need to be checked in the full, I would say, 3D simulations. So although there is this interesting possibility to generate magnetic field in these scenarios, but one has to check two things. One is the viability of this back reaction supported attractor, which I'm mentioning in the earlier slide. And we did not look at much about what evolution of this SU2 field after inflation. We just consider it like it decays as like a radiation species, but that is also something one need to see to maybe make more strong claim about the magnetic genesis in these models. And one important point which has been highlighted in the recent study, that we are basically studying the system in this regime where the back reaction of these perturbations are important, and the authors find out that so when the back reaction, so basically the coupling scenario where the back reaction is important and where the perturbative regime breaks down are roughly at the similar level. So one has to see like since we are studying the system in the perturbative regime, will that hold for these coupling, so these scenarios which we are considering. With this, I would like to end here and I'm happy to take questions at this stage. Thank you very much for listening.
Okay, thank